This lesson on descent performance will focus mainly on the forces in the descent and what factors govern the descent. In a normal flight, the descent will occur at a point we define as the top of descent, which may be up to 200 miles before the destination aerodrome. A descent will also be required following engine failure or depressurization. In this latter situation, the descent is forced early, and it is important for the pilot to be aware of what determines the characteristics of the descent so that obstacle clearance can be maintained. There are two ways of measuring the descent performance of an aircraft, either by angle of descent, sometimes called descent range, or rate of descent, sometimes called descent endurance. Firstly, let us consider angle of descent. Shown here is an aircraft in level flight with the forward forces balancing the rearward forces. Thrust in this case is balancing drag. In order to initiate a steady descent, thrust is normally reduced. Notice that the rearward force of drag exceeds the forward force of thrust and the aircraft slows down. The value of drag that exceeds the thrust force is called excess drag. In order to balance the forces and maintain speed, the nose is lowered until the weight apparent thrust provides enough forward force to balance the excess of drag. Now the aircraft will maintain this steady descent angle at a constant speed. The forward and rearward forces are in balance once again. Notice that the drag force is being balanced by both the engine thrust and the weight apparent thrust. The weight apparent thrust can be calculated by multiplying weight by the sine of the angle gamma. If thrust were reduced even more, then there would be a greater amount of excess drag. More weight apparent thrust is therefore needed to balance the greater amount of excess drag. To gain more weight apparent thrust, the aeroplane nose must be lowered even more. The result is an increase in the descent angle. For the purpose of the examinations, lowering the nose is also described as decreasing the pitch angle. From this demonstration, it is clear that it is the excess drag which determines the angle of descent. Notice that the angle gamma is the same angle as the angle of descent. Rearranging the formula on screen so that angle gamma can be calculated gives us the formula for the angle or gradient of descent. Drag minus thrust will give excess drag. In summary then, the angle or gradient of descent is controlled by the excess drag. In order to visualize this excess drag, it is necessary to return to the thrust and drag graphs that were used in the climbing lesson. Shown on screen are the thrust and drag curves for a jet and propeller aeroplane. We have learnt that in order to descend, there has to be an excess of drag. On the graphs, excess drag can be found by taking the area beneath the drag curve and subtracting from it the area beneath the thrust curve. The highlighted areas represent excess drag. Notice that if thrust is reduced at any given speed, then excess drag increases. Therefore, the descent angle increases, just as was shown on the forces diagram. If it were a performance priority to maximize the angle of descent, then from the theory we have seen so far, we would have to maximize excess drag. If thrust is reduced to 0, notice that the excess drag area is a maximum, but to obtain the maximum excess drag, the aeroplane needs to be accelerated to a very high speed, as shown. This can be achieved by closing the throttles and continuously lowering the nose of the aeroplane so as to cause the increasing amount of weight apparent thrust to accelerate the aeroplane. As speed rises even more, both the excess drag and the angle of descent will increase. The angle of descent, then, is a function of excess drag. The greater the excess drag, the steeper the angle of descent. This angle can be increased even more if it were possible to increase the excess drag. This can be achieved by deploying drag devices such as the speed brakes and the undercarriage, but attention must be paid to their maximum deployment speeds. The practical side of increasing drag to increase your descent angle occurs mainly in training and occasionally in commercial operations after air traffic reroutes. Take note that any increase in excess drag, either by deploying flaps or undercarriage, or by reducing thrust, will steepen the angle of descent. You have just learnt that to maximize the descent angle, excess drag must be maximized. In this part of the lesson, you will learn how to minimize the descent angle. Following an engine failure, the aim is to ensure that the aeroplane will cover the greatest horizontal distance so that the pilot has a large area in which to select a suitable landing field. This can only be achieved by using the flattest possible angle of descent, sometimes referred to as the minimum glide angle. To understand how this can be achieved, let us return to the aircraft in straight and level flight. If the engines were to fail, then to balance the excess of drag, which in this case will be the entire drag force, the aeroplane's nose must be lowered by a sufficient amount to create enough weight apparent thrust to balance the excess drag. The aeroplane will now maintain a steady speed in the glide. If drag were to be decreased, then notice that weight apparent thrust can be decreased by raising the nose by an appropriate margin in order to decrease the angle of glide. From this you can see that if drag were reduced to a minimum, the angle of glide will also be reduced to a minimum. This can also be seen in the graphs. Notice that VMD is the speed found at the bottom of the drag curve. At VMD, drag is at a minimum. Therefore, to descend at the minimum possible angle, the aeroplane must be flown at VMD. One of the other ways to examine glide performance is to consider the aeroplane's lift-over-drag ratio, commonly referred to as the lift-drag ratio. However, before we do this, there is a little more detail on the forces diagram to discuss first. Notice that in the glide descent, the resultant of drag and lift balances the force of weight. From your Principles of Flight lessons, the term for the resultant of lift and drag is total reaction. If the drag force line is moved upwards, you can see that we now have a triangle of forces, with the angle gamma being the angle between the lift and total reaction. From the bigger picture, which shows the aeroplane's glide angle with respect to the ground assuming no wind, it is easy to prove geometrically that the angle gamma is the same as the angle between the aeroplane's glide path and the ground. Consequently, from the triangle of forces, it is clear that if there were any change in the lift and/or drag values, both the angle gamma and the glide angle would change. A typical modern jet has a maximum lift-drag ratio of about 19. Where this ratio reaches its maximum value, the angle gamma will be at minimum. The lift-drag ratio reaches its maximum value at 4 degrees angle of attack and at the speed VMD. Therefore, VMD is the speed for the minimum angle of descent or the minimum glide angle. VMD is also known as a speed for LD max. The angle of attack at VMD is fixed at 4 degrees. If the angle of attack is greater or less than 4 degrees, the speed will change, the lift-drag ratio will decrease in value, and consequently the angle of glide will increase. If, following an engine failure, you fly at VMD, your aeroplane will be flying at the flattest possible glide angle. Never try to stretch the glide by raising the nose of the aeroplane. If you do so, the speed will decrease and the glide angle will steepen. At any speed other than VMD, your glide angle will be steeper than the optimal glide angle. Shown on screen is the angle of glide at VMD. The temptation is to raise the nose a little. This gives an impression from the cockpit that the glide is being extended. Looking at the diagram, if the nose were raised, the weight apparent thrust would decrease and the aeroplane would slow down. As a result, the aeroplane would not be flying at VMD and therefore not have the best lift-drag ratio. The result would be a steeper descent angle despite the fact that the aeroplane had a slightly higher nose attitude. Be disciplined in following the procedures for flying at the optimum glide angle as laid down by the manufacturers or the operator in the aeroplane flight manual. You may recall we mentioned at the beginning of the lesson that there were 2 ways of assessing the descent performance. We have covered the angle of descent, or descent range. Now let us consider the rate of descent, or descent endurance. You have already learnt in an earlier lesson that the rate of climb was a function of both climb angle and velocity. Similarly, the rate of descent is a function of descent angle and velocity. Shown here is the angle or gradient of descent formula that you've already learnt. All that is needed is to add the velocity function as shown. This is now the formula for the rate of descent. You may recall that force and velocity gave us power, so the correct formula for the rate of descent is the one shown. The rate of descent is equal to the power required minus the power available divided by the weight. Power required minus power available gives excess power required, so for any given weight, the rate of descent is determined by the excess power required. The greater the excess power required, the larger the achievable rate of descent. Conversely, the lesser the excess power required, the smaller will be the rate of descent. In an emergency descent, for instance a descent initiated by the pilot following depressurization, the aim is to reach flight level 100 as soon as possible. The regulations state that flight level 100 must be reached within 10 minutes. To achieve this requirement, the aeroplane would need to lose height with the maximum possible rate of descent, which can only happen if the aeroplane has maximum excess power required. Shown here are the power required and power available curves for both the jet and propeller aeroplane. The areas beneath the power required curves but above the power available curves represent the excess power required and are highlighted in light blue. In order to create the conditions of the greatest excess of power required, power available must be reduced to nil, as shown here. Notice that the blue areas of excess power required are now as large as possible. In order to achieve the greatest rate of descent, the aeroplane needs to fly at a speed that achieves the greatest excess power required. It is obvious from the graph that this can only be achieved at very high speeds. Remember that power required is a function of speed and drag. Therefore, the aeroplane needs to be configured for high drag and high speed in order to achieve maximum power required. In fact, for a lot of Class A aeroplanes, emergency descents are flown at maximum operating speeds with air brakes or speed brakes deployed and thrust at idle. If it were the aim to descend at the lowest rate of descent, the aeroplane would need to fly at a speed that gives the minimum excess power required. On the graphs, this point is plain to see. In fact, it is found at the very bottom of the power required curve. You may recall that this speed is called VMP. So to lose height at the slowest possible rate of descent, the aeroplane would need to fly at VMP. The lowest rate of descent is also known as maximum descent endurance, which essentially means the aeroplane will take the greatest time to descend. Let us now examine what factors will affect and modify the angle and rate of descent. The first of these factors is weight. For the moment, let us assume a normal descent at zero thrust whilst maintaining a standard scheduled descent speed. Looking at the diagram, a heavier aeroplane will have a greater weight apparent thrust. This creates more forward force than rearward force, and the aeroplane would accelerate. Therefore, in order to maintain the same speed and to provide extra lift to balance the weight, the aeroplane's nose must be raised. This increases the angle of attack and therefore the lift, but it also keeps the forward force of weight apparent thrust the same as the excess drag. Therefore, a constant speed is maintained but at a shallower angle. So under normal conditions, at a constant speed, an increase in weight decreases the angle of descent and therefore decreases the rate of descent. However, descent profiles are complicated as some aeroplanes, namely Class A aeroplanes, change their speed characteristics constantly during the descent profile. Let us now examine what factors will affect and modify the angle and rate of descent. The first of these factors is weight. You may recall that in order to achieve the minimum angle of descent, the aeroplane needs to fly at VMD, which gives the best lift-drag ratio and an angle of attack for 4 degrees. If mass is increased, VMD is increased. Therefore, our heavier aeroplane needs to fly faster to attain VMD. This concept will be shown through this next sequence. A heavier aeroplane will have a greater magnitude of weight apparent thrust. If left unchecked, the aeroplane will accelerate to a higher speed. As the speed increases, lift force will increase, but so will the drag force. Eventually, there will be enough total reaction to balance weight and enough drag to balance weight apparent thrust. At this point, the forces are balanced and a new higher steady speed is attained. This new higher speed is still VMD and the angle of attack is still 4 degrees. As you can see, the angle of descent has remained constant throughout. You may recall that increases in weight cause both the drag and power required curves to move up and to the right. Remember that this has the effect of increasing the speeds. Therefore, with higher weights, VMD, the speed for minimum angle of descent, and VMP, the speed for minimum rate of descent, will both increase. In summary, therefore, weight has no effect on the minimum angle of descent, but it will increase the speed along that descent gradient, and therefore it will increase the rate of descent. The next factor to affect the angle and rate of descent is the aeroplane's configuration. Looking at the diagram on screen, if the flaps or undercarriage were deployed, then excess drag would increase. To balance this increase in excess drag, the nose must be lowered. This action increases weight apparent thrust and a balance of forces is restored, but more importantly, the balance is achieved at a higher angle of descent and therefore a higher rate of descent. The effect of configuration can also be seen using graphs. Shown here are the drag curves for the jet and propeller aeroplane with excess drag shown by the light blue area. With flaps and undercarriage deployed, you will recall that the curves move up and left. This has the effect of increasing the excess drag and therefore increasing the angle of descent for any given speed. Notice too that the speed for the minimum angle of descent, VMD, is lower. The same effect can be seen when examining the rate of descent and by using the power required graphs. Similarly, the light blue area represents excess power required. With flaps and undercarriage deployed, you will recall that the power curves move up and left. This has the effect of increasing the excess power required and therefore increasing the rate of descent. Notice too that the speed for the minimum rate of descent, VMP, is lower. In summary then, with gear and flaps deployed, the angle and rate of descent increase, but the speeds for minimum angle and minimum rate of descent decrease. The last factor to affect the angle and rate of descent is wind. The diagram shows a descent angle and descent range with no wind. If there is a headwind blowing, the aircraft will move backwards relative to the no-wind diagram. This steepens the glide angle and decreases the descent range. However, notice that the aeroplane reaches the same descent altitude in the same time as the aeroplane flying in zero-wind conditions. This demonstrates that a headwind, which steepens the angle of descent, has no effect on the rate of descent. Conversely, if there was a tailwind blowing, the aircraft will move forwards relative to the no-wind diagram. This flattens the glide angle and increases the descent range. However, notice that the aeroplane reaches the same descent altitude in the same time as the aeroplane flying in zero-wind conditions. This demonstrates that a tailwind which flattens the angle of descent has no effect on the rate of descent. The effect of the wind on the angle of descent can be examined a little further. Because of the adverse effect of the headwind on the angle of descent, then in a glide, it would be of a benefit to increase the aeroplane's forward speed slightly. This has the effect of reducing the time spent in the headwind. This means that the aeroplane will not be pushed back as much by the wind. Similarly, with a tailwind, because a tailwind benefits the glide by decreasing the glide angle, it would be better to try and stay in this situation for longer. So this time the aeroplane's forward speed can be decreased so that the aeroplane can stay under the tailwind effect for longer and therefore be pushed further forwards. When flying on a training sortie, make sure you know the wind speed and direction, both for the surface and aloft. This will help you plan a better descent, giving you more accurate circuit patterns. But more importantly, knowledge of what the wind is doing will ensure you obtain maximum descent performance if an engine failure should occur. This completes the lesson on the general principles of descent. In this lesson you should have learnt the difference between angle of descent and rate of descent and the factors that determine them. Whilst most descents will start at a scheduled predetermined point called top of descent, and they will be uneventful, there will certainly be occasions when a pilot is rerouted and in the worst case suffer an engine failure. Under these circumstances, your knowledge of descent performance will be vital to ensure you carry out the correct actions and clear obstacles during the descent. More detail on the descent performance of different aeroplanes and the regulations that apply to these aeroplanes in the descent will be covered later.